Hi, and welcome to the third in the series of podcasts on realistic business forecasting. We're going to be spending a good deal of time in this and future podcasts looking at historical data. Because unless we actually know what the historical data is telling us, it's going to be difficult for us to actually make any sensible forecasts. Now, the first aspect we're going to be looking at is correlation. So why are we examining historical data? I cannot emphasize this enough. We need to know where we want to go. We must know from where we have come. A little bit of philosophy from yours truly. It might sound a bit fanciful, but it is critical to everything we're doing in these podcasts. So there are some key questions which I hope to address during the course of this particular session. First of all, what variables are affecting our demand? And we'll use demand as the general variable because it's going to be a critical one for business forecasting. And how much influence do these other variables have on our demand? Now, time is often an important variable, but that is a big subject in itself. So we'll leave time out of it for this particular podcast. Next, we want to know if there is some influence, how the variables are actually related. Is it a straight line relationship or is it something else? Far too often, I've seen firms just use a very simplistic method which assumes a straight line relationship. And as a result, the forecasts are nonsensical because the relationship clearly is not simply linear. And the third question on this set is whether correlation implies causation. I've got some good examples lined up for that. I also want to address this issue of sample size. Why is it better to have as many data points as possible? Because pretty much all forecasts are based on sampling, and this will be a recurring theme throughout the podcasts. And something which is not often taught, but which is quite important is when you have generated the correlation coefficient, how significant is it? So let's crack on. Now here, we've got three extreme values of a correlation coefficient. We have pretty much perfect correlation. The maximum value is 1, so a correlation of 0.99 is pretty much perfect. And a good example here is perhaps, say, hours of sunshine versus ice cream sales at a seaside resort. The warmer and sunnier it is, the more likely you are to make ice cream sales. Now, the lowest value of a correlation is -1. So in the second diagram, when you have a correlation of -0.98, a good example of that is, say, rainfall and ice cream sales. So the more rainfall there is, in other words, the worse the weather, the less likely you are to sell ice creams. And the third example is an example of pretty much no correlation at all, two completely independent variables. And as an example, I've got the number of engineering PhDs awarded per annum versus mozzarella cheese consumption. Now, I'm sure no one would agree that there is any relationship between those two variables. And yet, if you actually look at the data, you can see that these two particular variables are very highly correlated, a figure of 96%, which is pretty much as good as you can get. So this is an example of a spurious correlation, and I provided a link at the bottom of this slide. And there's some quite hilarious examples of two variables which are seemingly correlated, which have absolutely nothing to do with each other. Now, is correlation the same as causation? Well, sometimes, but not always. If we take a look at the top two pictures, we can see the yields for two particular crops, corn and soybeans. And what happens is, as the temperature increases, then the yield of each of these crops go down. It's not a perfect fit. You can see there's some scattering around the line, but nonetheless, the trend is definitely downwards. As maximum temperature increases, the yield declines. So now no one is going to say that as yields increase, temperatures will decline as a result. The causation there is quite clear. It is temperature affecting yield. But look at the bottom example, which is perhaps more relevant to us in business forecasting. Inflation and interest rates. Now, this is quite a tough one, because what happens is, if inflation is high, which is what we've seen at the moment, a government will increase interest rates. So they could argue that the correlation is positive and the causation is positive. But then as interest rates increase, inflation should decline. That's why central banks do put up interest rates. So they're going to have a negative correlation, and the interest rate is causing the inflation rate to decline. So it is quite complex. Does inflation affect interest rates or vice versa? That is something which we will have to deal with in the future, but let's just leave it for now. Now, let me come on to one of my many bugbears in forecasting, what I call the 0.7 fallacy. A good deal of textbooks, and I've seen this in courses as well at universities, in the material written by the lecturer, suggests if you have a correlation greater than 0.7 or below -0.7, then that's a good figure and you can say that's acceptable. But it's not actually that simple. A good correlation between two variables depends not only on the value of R, but it also depends on how many observations you've got. And like with any sample, the more observations you have in your sample, the more robust your results are going to be. Now, there is a statistic which actually does test how significant a value of R is, whether one value of R is better than another. And in particular, whether an R value which we've generated is significantly different from 0, because if it's not significantly different from 0, the conclusion you would draw is that there is no relationship between two variables. So let me share with you this slide, which is actually based on one of my recent experiences in the commercial world. The clients generated a correlation of 0.7 based on 13 observations. And he was quite happy with this. And he did not like my correlation of 0.45. He said, oh, yeah, your correlation's much lower than ours, therefore our results are better. And I said, well, hold on. I've actually got 84 observations in my data set. You've only got 13. So how do we actually compare these two sets of data? Well, on the left here, I've derived the test statistic, which is, say, a little bit complicated, but what I did, I just developed a simple spreadsheet, and I generated the value for the client 3.25 based on this statistic, and the N and the R are what is used in this formula. Now, this test works on what is called a critical value, which I won't go into details of for now, but what we're testing is whether the figure we have generated is greater than the critical value. Now, for the client, the answer is yes. So the R of 0.7 is significant, so that's a good start. Now, how much better is the figure generated from this test statistic better than the critical value? It's about 1.07 greater. Okay, so we'll put that to one side. Now, I did the same calculations on my analysis, and I generated the test statistic of 4.563. My critical value, because I have got more in my data set, is a bit lower than the client's critical value. but the difference is 2.57. So in other words, even though my R superficially looks worse, the result of this correlation is actually better because I have a much larger sample size. Now let's look at another set of data here. And I've just generated two sets of numbers. Series A is just -10 to +10, so there are 21 observations in total with increments of 1. And Series B, which looks as though it declines for the first half of Series A and then increases for the second half. And if you just do a bog standard correlation calculation, then you get an R of 0.43. And in fact, that just fails the significance test from the previous slide. So we would draw the conclusion that the correlation between these two series, A and B, is not significantly different from 0. However, if we actually draw out the data, as I've done here, you can see that the two data sets are perfectly correlated, and they are correlated not in a linear manner, but using this formula here. It's one I just generated at random. And this points to a critical lesson, which is before you do any analysis on data, have a look what the data is telling you in graphical form. So here it's clearly not linear, but it does look like a particularly strong function, and it's a cubic function. So what can we actually draw from these lessons which I've presented in this short video? First of all, I've found it useful to have some sort of hypothesis in mind. I'm not suggesting a formal hypothesis, but just have some idea of how you expect the relationship to be. For example, if we look at crop yields and weather, you generally expect if the weather is good, yields will be higher. If the weather is poor, yields will be lower. So if you've got a relationship which is different from that, you need to do rather more investigations. Now, I hope I've also demonstrated in this little podcast that correlation is not the same as causation. Causation is a big subject, and we will be dealing with that in future podcasts for sure. Third point, sample size is critical in so much of what we'll be doing in these podcasts. And it is as critical to correlation as the value of R itself. And that my test formula showed that, I hope. And the last thing is, before you actually put pen to paper or fingers to keyboard, as it is nowadays for most of us, just actually eyeball the data. Put them on a scatter diagram or a bar chart or whatever you like, and just see what does the data look like. Very often, for example, you might get one point which is completely off the charts. And when you then decide to analyze the data, you might think, well, actually, this is an error, this point, so we're going to remove it from further consideration. So it's always useful to do a picture first before doing any analysis. Well, I hope that has given you all food for thought. I will be looking at correlation on more than one occasion in the future for forecasting because it is such an important part of what we do. So thank you for listening. If you have any comments or queries, as always, put them in the comments box. And bye-bye for now.